Dr. Matthew Wolford from NRL, Naval Research Laboratory in the US. I'm going to give a little introduction, a little bio sketch. Yeah, Dr. Wolford is the head of the Electron Beam Science and Applications section at the NRL. And the Electra facility that they are working at is a 500 kilovolt counter propagating with a rep rate of about 5 hertz, an electron beam. And they formerly use this for the development of KRF. For those unaware, those are krypton fluoride lasers for inertial fusion energy. And they are also, in addition, doing research with argon fluoride for these lasers. He's going to tell us a little bit more about that, so I just want to get a little bit more of a detail. Dr. Wolford got his BS in chemistry at Binghamton University, New York, and then got his PhD in chemistry at the University of Pennsylvania in 2002. And it looks like he's been working with NRL for essentially the last, what is that, 20 years now? Is that right, Matt?
Yeah, before that as a contractor. Yeah, I've been here a long time.
Yeah, and so it looks like he's been doing some great work. He is the co-inventor of 4 patents, has over 100 scientific publications with a much larger H index than I think any of the postdocs or grad students are here. Yeah, so he's been since 2006, he's been the research chemist for the plasma physics division at NRL. His research has been kind of the electron beam, the pumped lasers, laser triggered gas switches, optics, a plethora of stuff, optical design, ultra fast spectroscopy, chemical kinetics. Yeah, so there's more than I could say. I could talk for a while, so just introduce you. I think you said you have a hobby of making maple syrup.
That is correct.
That's very interesting. I would ask many more questions about that, but instead, I'm going to hand it off to you since you are going to be talking about lessons learned and ongoing research at Electra, Rep Rate Excimer Laser Facility. So you have the floor. Thank you for joining us, Matt.
Well, thank you for the invitation. So, excimer lasers. I'm going to try to go through briefly kind of where we're at. Um, we have a lot of available technologies that are ready now. They're modular, they're scalable, um, driver components, including the solid state switches, the inexpensive pulse power, zooming for the laser to follow the target, and beam smoothing for target illumination. And excimer lasers tend to usually operate at short wavelengths. On the picture on the right, you can see a concept of some time ago of a laser fusion power plant that was envisioned. In this particular case, it was a driven by excimer lasers with a direct drive configuration with a solid wall and a pellet to generate electricity. And NRL's been kind of looking around at these various concepts for fusion energy for some time. And it's been great. We've had this explosion of private entities that have started the real hard work of developing the science and technology, the basic stuff that many years, for many generations previous to my involvement, looked at excimer lasers and are looking to use them to make inertial fusion energy power plants. And some of the things that are still needed to get to a power plant are a couple of the items I mentioned at the bottom of the slide. One is scaling to the fusion power plant size and lifetime. And that's both the size, how large of a laser energy, how much laser energy you're going to need, as well as the lifetime, which is probably on the order of 1 billion shots. Many component lifetimes have been evaluated and are very close to that. And I'll go through examples of where we're at with where NRL has the evaluations of what the lifetimes are so far. And then the other thing is we haven't had a successful excimer target gain implosion similar to the National Ignition Facility has for solid state lasers. We haven't, there hasn't been an excimer laser that's been built on the same scale as the solid state lasers. But the implosion simulations and the analysis of building such a facility looks extremely promising. And that's why we have people out there looking at this science and looking at this technology to develop it, and rightfully so. It looks like an excellent opportunity. So what is a krypton fluoride laser, or what's an excimer? So the name comes from excited dimer, which is actually kind of a misnomer, because really a dimer would be implied that you would have two krypton atoms or two fluorine atoms, and the Russians call it an exaplex because it's an excited complex. But over the years, the traditional way has been to use Excimer for krypton fluoride and argon fluoride and all the other laser wavelengths that we talk of this kind, where they have an excited state that has a complex, and quite often the ground state of the laser is dissociative. And this is because it's an excited when only the molecule or the atoms really combine together in the excited state. And that's what makes it very exciting. And that because you're able to have a ground state that's dissociative, you always have population inversion, which is a requirement to have a laser. So the fundamental wavelength here at KRF is at 248 nanometers. We generate that by putting energy into the gas, creating krypton and fluorine, having them to combine to create this excited state, and then eventually they have a collision and they produce a photon that happens to be at 248 nanometers. Discharges, lasers have been used routinely in industry for chip lithography, amongst many other things. And discharge lasers are predominantly the most common utilized excimer laser technology that you'll find. When people typically talk about excimer lasers, they're talking about discharges. That's what people have, their experience are. And that's a very common and useful thing for a lot of different technologies. But what I'm going to talk about today is a little bit about something we use to make one way to make large uh, excimer lasers, and that's using or pumped with electron beams. They share several technologies that are similar to commercial systems, but they require R&D for electron beam science and technology due to their larger size. So just to give an idea of what it looks like, an electron beam system looks like the slide that's presented here. You have pulse power on the left and on the right, or if it's counterpropagating. But that pulse power creates a cathode. It goes into a cathode. In this case, it's 500 kilovolts is the voltage. That's 500,000 electron volts is the voltage. And then it emits electrons from the cathode in a region that's under vacuum through either an anode or through a structure that we call very exotically hibachi. That looks like a grill, just like a grill that you would put your hibachi or grill on, and you support a foil or electron beam window, and it puts the energy into the laser gas. And that aspect of putting the energy into the laser gas by this very large electron beam then creates a laser medium made up of krypton fluoride excimers in the purple region here. And then you extract the energy from an input beam, or you can make an oscillator, but quite often you extract the beam with an input beam, and then you get gain, and then you measure the output. And for KRF, we use krypton and argon to stop the electron beam, and also for the higher efficiency, we adjust these parameters. And the kinetics is a little bit complicated. I'll talk about that. But for rep rate, we also have this thing that's a laser gas recirculator. So this recirculator moves the laser gas so it's very available to run at repetition rate, which would be needed for a fusion power plant. You'd be able to fire readily, replacing the gas, and the electron beam fires into new set of gas between each shot. And this is very large. I didn't give it a dimension here. The scale of this window, for example, is typically on the order of 30 centimeters by 30 centimeters, or it could be larger, like on the scale of a meter in dimension. And this is the type of design that we're talking about when we talk about electron beam pumped excimer lasers. And this type of technology has also quite often has a magnetic field to help keep the electron beam inside the laser gas, which happens to be a plasma from this 500 kilovolt electron beam, 100 kiloamps, a lot of energy, and then we extract the energy out. So at NRL, we have some experience with these large electron beams. On the top, I show a picture of Electra, which is the facility I work on, which can operate at 5 hertz. For KRF, it operated between 400 and 750 joules of laser light per shot. Um, and like I said, the aperture of the window is 30 centimeters by 30 centimeters. The electron beam is 30 centimeters by a meter. Down below is another facility at NRL called the Nike facility, which is able to, it's even has an electron beam amplifier that's even larger than Electra. It doesn't run at rep rate, but it's larger in energy. It produces a 3 to 5 kilojoules of laser light. It's at a higher voltage. It can operate at a higher voltage of 750 kilovolts, 500 kiloamps, and 240 nanoseconds. And it has a window that's roughly a 60 centimeter by 60 centimeter aperture. And the benefit of having these different size machines is we're learning how these machines scale, as well as how these machines operate at different sizes and scales so that we can adequately try to interpolate as much as possible and extrapolate very little in designing the components for a fusion power plant. So we use these tools to learn how electron beam pumped lasers work and how these large excimer lasers can be built. So this is a view graph from 2012 that shows that in 2001, our rep rate was roughly once every 20 minutes. By 2011, we thought we operated at 2.5 hertz to 5 hertz, 5 pulses per second. We think a power plant at that time in 2012 that the requirement was going to be 5 pulses per second for a fusion power plant. We showed that the predicted efficiency in 2001 was less than 2%. By 2011, we thought based on our measurements that we could get a wall plug efficiency of 7%. That includes all the energy that is needed by the for KRF is needed by the ancillaries, the pumps, the electron beam, and everything is all encompassed in that 7%. There are a couple things that are removed. We were thinking at the time that magnets, that high temperature superconducting magnets will be around by the time that the fusion power plant is going to be built. That may be, but that doesn't count for how much power is in the magnets. And it also looked at trying to minimize the amount of energy in the flow loop or the recirculator. But our guess was that we would need a predicted efficiency of greater than 6% to be viable. I should point out that another requirement is the dollars per joule. Lower is better. The cost of building these drivers, if the driver is going to cost a couple $1 billion, not many people are going to build them. So you need to try to figure out how to make them as cheap as possible. Our durability on a foil in electron beam pumped lasers was in around 2001 was around 200 shots. By 2011, we had 90,000 shots continuous at 2.5 hertz for a 10-hour duration run. And we still have somewhere to go. We need to get 300 million shots for a power plant. And I think I may or talk a little bit about why the limitation in 2011 was 90,000 shots and why we think we have the technology that goes a lot longer than that. And most of these advances have been made through understanding and controlling the relevant physics as much as we can to try to get the technology viable for a fusion power plant. So, like I stated before, on the left is a picture of Electra, and I'm mentioning again, which I mentioned on the previous slide, that we had 90,000 shots continuous at 10.5 hertz for 10 hours. But that's just the number. So the other aspect of this is the panel on the right shows that when we fired at a with a very high efficiency strip cathode, we were able to show that we could reproducibly and reliably get over 700 joules per pulse at 1 hertz. That's continuous right there is the blue dots. Then we stopped, took a pause, got the machine ready to run, operate at 2.5 hertz the same day within probably the same hour or so. Started again, and we showed the pink squares in the top right panel to show that we could operate at 2.5 hertz at 700 plus joules for every shot. Now, the technology for going long time, we typically used monolithic cathodes, and they have lower output energy, uh, roughly 300 to 400 joules. On the below is a rep rate run with a monolithic cathode of 30,000 shots, showing that the pulse energy is quite reproducible, showing an example, or it's actually the shot at 10,000, 20,000, 30,000 to show how much the intensity varied in an oscillator configuration. And then throughout this talk, if you want to find more information, there should be notes or slides at the bottom where there's citations if you want to read the scientific literature. So electron beam transport from single shot to rep rate had a lot of different changes. Okay. Single shot electron beam diodes have something called a transit time instability that creates the electron beam to go everywhere else. Quite often, typically they used monolithic cathodes, which means that you have electron beams that slam into ribs. Sometimes, quite often they've used in 2001, everyone was using an anode where they use an anode for the electron beam to transport, and then a pressure foil, which goes into the pink area. And that anode does two things. One, it has a transmission loss, but also creates scattering of the electrons, so they also scatter into the ribs. And then additionally, whenever you have the pressure or your laser gas, when you go into the laser gas, you have backscattering from the pressure, from the gas, as well as a transmission through the pressure foil. So to be highly efficient and for a long durability rep rate, you want to remove as many of these things as you can because they all cause heat loading. In this environment that I'm talking about here, the electron beam diode is in a vacuum. It's under 10 to the minus 6 torr. So that's very difficult to cool things that are warm. Once they're warm, it's going to be very difficult to remove them. So we use the laser gas to remove convection to take out heat on the foil side, and then the ribs or the hibachi ribs, which are pictured, there's three of them in this picture, have a shape inside that can be water cooled. And unfortunately, conduction cooling isn't very efficient, and quite often, most of the cooling that you get is from convection from the laser gas. But Electra showed that removing the anode foil and patterning the E-beam for small spacings got to be high efficiency. And here's some pictures of a velvet cathode with some bars show that with radiochromic film to show that we were able to transmit the electron beam energy in. I previously showed you this was the technology that allowed us to get the very high 750 joules per pulse with a minimal electron beam of 500 kilovolts and 100 kiloamps for 140 nanoseconds. And down below is the magic simulations to show that we had a pic code that was pretty good of showing what the representation that we had of the basic physics of how this worked. Also, I should mention that the gas constituents play a role in the electron beam efficiency. Basically, the gas, how much backscattering you have, what the gas constituents determines how much electron beam efficiency you have in the gas. It turns out that the greater the percentage of argon and the smaller fraction of krypton actually allows a greater efficiency of the electron beam into the gas. That may or may not be the same as the best condition for you to get the best kinetics efficiency from the energy you're putting in the gas and creating the KRF molecule in this case. But what happens is this efficiency ends up being, from our experience, the dominant efficiency because it's considerably more energy you put in the gas. So you get more energy coming out for the same size electron beam. So that's why we use a buffer gas such as argon to try to. One of the reasons is not only from a kinetics point of view, but also to increase the efficiency of the electron beam into the gas. Now, the KrF gas is very complex. This Orestes code here at one time, I think eventually it had more, but right at this time had 24 species and 144 reactions. It's pretty much simplified in the bottom left corner here with this neutral channel and the ion channel. The electron beam creates both excited argon and krypton atoms as well as uh, ions of argon and krypton. And both of those eventually create the molecule of KrF. And then you have a bunch of reactions that remove the energy from the KrF, including reactions with argon and krypton, and generation of your photon removes the KrF, but that's the positive one we want. So all those things happen, and again, the transition of the KrF species is just 5 eV, and we're talking 500 kilovolts of energy. So we're talking 100,000 more higher voltage than is required for the lasing action. So there's lots of reactions that can cause all sorts of problems and inefficiencies. And the intrinsic efficiency that we measured at NRL is roughly 12% for KrF. And that's the best we could do with an electron beam pump system at roughly 500 kilovolts. And so that energy gets down there and settles in the KrF molecule, and then we extract it. If we could get a higher efficiency, that would be very beneficial for fusion power plants. Just to show on the bottom right, after some adaptation, you can still see that over time, even with Electra data and codes, the codes and data have relative agreement, but there are still discrepancies. And we're still always trying to adjust the rates to try to understand this very complex system to match up with the data that we have seen. So the other thing I should mention is we did show 730 joules with an electron beam power deposition profile. On this top left, it shows the power in kilowatts per cc, which was roughly peaked at 700 kilowatts per cc. This is the dotted line of the electron beam. The blue line is our simulation of the Orestes code. And this lighter blue line, or maybe it's green, I can't tell, is the laser experiment profile. And so this is how we're trying to compare the code. In addition, we tried to amplifier, and we had a 15 joule and a 25 joule input, and we compared the various timings to try to get how effectively we could measure the energy out of the system. I apologize, the data doesn't seem to be here, but most of the data we had was around for this amplifier system when we ran Electra as an amplifier was around 500 joules, so it would have been in this area here. And it was difficult to tell the difference between the timings and the input energy to get that exactly right. So there's still a little bit of work that could be done in improving code of the KrF molecule. One of the couple of lessons we learned along the way is we learned that we didn't understand the reaction of the electron beam and whether, we created fluorine atoms or fluorine ions. We went through this whole discussion of whether we had dissociative attachment versus superelastic. Um, we decided that our model seemed to agree with dissociative attachment. There was work by Dr. Peters in the Netherlands that did some small electron beam work that was very, very informative about this type of reaction. And you can see that it was difficult for us to understand the fluorine abundance of the model because when we had it originally, we found that where we could operate at low, if we went to dissociative attachment, we were able to have higher efficiency at lower fluorine concentration for 248. And that's beneficial because fluorine, F2, does absorb at 248. Also, on the right, we looked at helium as a possible buffer gas in the laser system because we thought that that would be very useful in terms of cooling the laser gas over long rep rate runs. And we were able to show that we were able to get close to 700 joules or over 700 joules, even with a substantial fraction of helium. So that's from an engineering point of view. We looked at adding helium to increase the thermal conductivity so that we could take more heat out of the system so we could go at either higher rep rate or for longer duration in keeping the laser gas cooling. So we started exploring from an engineering point of view how it impacted the scientific results. And that's what these companies will be doing as they develop their fusion power plants. They're going to try to optimize both engineering constraints and physics constraints and basic science constraints to try to optimize what is the best way to make a fusion power plant. So another thing we looked at in terms of engineering is developed a recirculator to both cool and quiet the laser gas. And so this laser gas went around at a nominal 5 meters per second. It's quite large. It's 90,000 liters. And because of the angular multiplexing configuration that we were using at NRL or been looking at NRL, we said that for us to, so that we didn't have any perturbations to the laser beam as it propagated over long distances, that we controlled our variation, our delta rho over rho, our pressure differential over the total pressure of the gas. I'm sorry, our pressure, our density variation, delta rho, density variation over the whole density of the gas. Our goal was to be around 10 to the minus 5. And so what we figured, calculated that that would have enough optical quality that you would be able to run for a fusion power plant. And so we looked at trying to see how well we can maintain a laser beam focal profile at rep rate by using a probe beam surrogate as we fired the electron beam at 1 hertz and also at 2.5 hertz. Those are the two panels on the right. And you can see that there is some variation at 2.5 hertz on the 500 micron spot and intensity variation. We think that's controllable at that rep rate, but it is better at a lower rep rate. And those types of intensity non-uniformities could cause laser imprint on a direct drive target or other types of laser imprint. So we're trying to control the focal profile so that we have complete control from a laser building point of view, so we can deliver what a target physicist would want on their target to have a successful implosion. So we have pretty good control at rep rate, and we do have ways to improve this by either increasing the flow, that will one way to improve the profile, or increase the time is another way to help the profile be sustaining at a rep rate operation. Another thing is to control the long lifetime is to minimize voltage reversals in electron beam diodes. So this is more of like lessons learned, which was the title, is we learned that when we had the voltage reverse, meaning that instead of being the cathode emitting electrons that actually the hibachi tried to emit electrons because we went the other way. That was catastrophic because the when the voltage reversed, the material that was designed to emit uniformly on the cathode is not designed to emit uniformly by the hibachi or the foil structure. And then one singular point could send out a tremendous amount of use all the energy comes out from one little spot, even if it's 1%, and that can create a pinhole, as you can see in the upper right. So we've came up with a lot of ways to remove this initial electron beam mismatch, which we could do by increasing the anode cathode gap and or other types of techniques. But we also found in Electra's case that we had a reflection that was on the 10 microsecond time scale, and that reflection on that time scale could cause problems and stop our operation. And also where the ribs were, the hibachi structure, where the cathode faced the hibachi structure, underneath the velvet, we would create pitting, as shown here in the lower middle section. We would get damage. So we would see damage from the reverse voltage back onto the cathode, eventually damage the cathode, and then prevent the longer lifetime of the cathode. We were eventually able to get to 250,000 shots reliably by our cathodes. But these are the damage mechanisms we learned. And so we realized that voltage reversals were very bad and we needed to minimize them for long durability and for long operation. But the problem we have is that in Electra is we have a initial first of a kind rep rate system that had laser triggered spark gap switches. And it did well for the cases here on the left. You can see we ran 90,000 laser continuous shots at 2.5 hertz. These are kind of our records. Like this is what we could do. We got 150,000 shots on the same foils. We got 50,000 shots on the same foils at 5 hertz. We did 300,000 laser shots in 8 days of operation. We could show that we could do rep rates, but it's still not at the billion shot scale. And the problem for Electra specifically is that in Electra, we have laser triggered spark gaps. And these laser triggered spark gaps over time, after thousands of shots, if you look in the bottom right, you can see over time, we would have switch runtime would increase, meaning the laser breakdown of the laser going into a volume full of SF6 with flowing gas, but it's got to go to a focus, and the laser beam doesn't focus and create a streamer between a cathode and an anode made of alkanite. And what happens is then the switch does not fire, a megavolt energy does not transmit or transmit at the wrong time. And when we have multiple parallel lines going into our cathode, those multiple parallel lines can create something in the top right here with this green curve shot 7,998. And that's called a unexpected voltage reversal because of a missed time shot. And so that means that the spark gaps, the laser triggered spark gaps, the laser's firing correctly in the back that goes in to tells the triggers to fire. The spark gap themselves did not fire at the proper time. And that's what turned out to be the limiting aspect of the foil and created the limiter on these records. Now, so the symptom is a hole by the foil. The cause was caused by these voltage reversals. So to get rid of, we want longer longevity foils. So to do that, we need to get rid of the thing that causes it, which was these laser trigger spark gaps. And so we looking at building an all-state pulse power demonstrator that ran 11 million shots continuous for 319 hours with solid state switches. And so this showed that solid state technology can operate reliably switches in there, and so that we can get to a solid state type of device and look with a magnetic switch, getting rid of laser triggered spark gaps. And by getting rid of the laser triggered spark gap and going with a other new advanced pulse power technology, our assessment is that the foil longevity will be much, much longer than we've been able to show because our symptom was the effect of our system having laser triggered spark gaps. So we are optimistic that it's possible to get much, much longer durability of the foil. And that is been one of the major challenges for electron beam excimer lasers for some period of time. The other thing is about scaling to a large size. The transit time instability is another factor or another piece of science. When you go to something that is a meter class size uh, cathode, it has some additional challenges. And so you have to realize that when you scale something from a small size to a large size, sometimes new physics come to light and you have to think about it differently. And so to solve this, you either segment the cathode or reduce your duration of your pulse to so the pulse is shorter, but you have options. There's options to solve this transit time instability. But when you just make things bigger, you just need to think through all your physics to make sure that the physics and the technology that you're still in the same realm that you were on a small scale. And so this is one of the things that happens when you make cathodes larger is you eventually get to a different regime where you have some additional instabilities and considerations to consider. Just briefly about technology here. Look, when we do these research, there's lots of different components on these types of large devices. There is, the velvet here that show 10,000 shots on the left. There's an SCM of that. Carbon's much better. It can go to 250,000 pulses without much damage. So we can synthetically make various things, and it's our ability as technology improves, it's our ability to improve our components by having more control and making it. The velvet here on the left is something people could purchase for their clothing. It's a black velvet. That's what it was originally made for. And we used it for cathodes, and it works great for thousands of shots or hundreds of shots and it works great. But if you want to go for a longer life, you have to worry about the epoxies, you have to worry about the structure. And so actually we looked at trying to get the same characteristics in our synthetic types of cathodes as that were very successful, were the very fast turn on time from the velvet that we observed that showed very good reliability and durability that we had in the Electra system. I mentioned before that you could do most of the cooling in the system is from convection. I just want to point out that there are many ways to do cooling from convection. One way is to have little bars on the inside of the ribs and blow gas against the laser beam. This is something that Georgia Tech did over 15 years ago, which showed that the average foil lifetime could be controlled below 400 C, and that we were able to send a laser beam through it, and we didn't see any decline in the energy in the bucket at 5 hertz for 500 shots. So it looked like it wasn't perturbing the laser beam. And these are the types of technologies that can be very helpful in building a large scale system and allow you to scale to larger sizes and because the convection from the gas alone, as it goes across a larger aperture, you have more and more pulling off as the gas goes farther and farther. It has a tendency to pull away from the foil, and you have different size turbulent zones. So briefly here, I just want to mention that we did operate Electra in a rep rate configuration. I mean, a angular multiplex laser beam. We had a preamplifier. We were able to get the laser beam through Electra, and it was around 500 joules per pulse. We were able to do this at 5 hertz for about 2 seconds. And we learned a lot from just doing that is just by doing things, you learn that, okay, the phase aberration from the preamplifier and the cooling in the preamplifier was more important than the main amplifier. So well, you learn where your problems are when by trying sometimes. You think you've solved one problem, then you realize, but when you execute, something else happens and you have to go and figure out what happened. Um, so we were able to make this laser amplifier work at rep rate. And then we just looked at it and we thought, okay, is there something we could do better? And so we were looking at trying to increase the wall plug efficiency. And so instead of KRF, we looked at ARF. It looked promising from an efficiency point of view. That's on the left side here. And then the target gain physics looks promising. So we've explored that. We've been exploring this argon fluoride as opposed to krypton fluoride because of the potential of having a higher wall plug efficiency and a higher target gain. It has some challenges. It has challenges with optics, the optics because the photon energy is higher. Optics probably will be more challenging or will be more challenging than they are at KRF or at an infrared wavelength, for example. So as you go to shorter wavelength, it has benefits from the target physics. That's good, but you also have to look from the engineering point of view what the challenges you are. But for NRL, this is a great project because it's basic science. We can go in, we can tackle it, we can evaluate how this is on a small scale and see the promise of argon fluoride. And we were able to get about 240 joules out of our system. It was designed for KRF, but we were able to get 240 joules. We were able to show that it has very broad bandwidth, which is a very good characteristic for laser plasma instabilities. And we think the wall plug efficiency could be 10%. So we're in the early stages of ARF, electron beam ARF. There hasn't been many people that have tried it, so we were evaluating it, and we were trying to see if it made worthwhile to evaluate further. And in that, we've also done a kinetics model for ARF, just like we did with KRF, and we had to change some important engineering components. One is the smaller cathode, which it has some advantages because we removed support structure, we decreased the cathode size, we increased the efficiency. It has simpler physics, no ribs to water cool, increased compactness, and increased modularity. So that was all very promising, and we did successfully implement a new type of foil, Beta 21S, over a meter without a structure support. That's on the top left. So it's possible, but this material does react with fluorine more vigorously than we like. So it's not ideal. We don't have a solution. But it is a way for us to evaluate different materials to see if excimer lasers could benefit, including KRF or ARF. But going down different paths lets you look and evaluate different materials from a physics point of view, from a point of view of getting an electron beam into the gas without having the structure of the hibachi in there. This is a lot easier to model. It's a lot easier to adapt. It has a lot of advantages, and we'd like to get to the situation where we have large areas without rib support structures to make it more efficient and easier to handle and the technology to progress at a faster rate. So, and then I should mention that because the ARF is a short wavelength and it has a broad bandwidth, we were just looking at whether this broad bandwidth could be made into a short pulse, ultra short pulse ARF laser. And this is something that we're looking at exploring further at the Naval Research Lab, taking an ARF beam and trying to have an ultra short laser uh, beam in order to get to do new physics because of higher energy photons to do multi-photon ionization and directional X-ray capabilities, as well as looking at it for other purposes. So it's something we're always exploring. We're always looking, trying to adapt things that we learn for doing fusion research and trying to adapt it also to other aspects of research that would be beneficial, we think, to pursue. And then I think this is my last slide. This is just a review of the status. I mean, we've made a lot of progress, and there's still progress to go, but well, things are looking bright. So, the electron beam pumped excimer lasers are modular. We showed that solid state switches could be helpful. We're looking for inexpensive types of ways to generate our laser systems so that it doesn't cost as much, so that we have more of them. They're more likely to be built. And we have the ability to control our laser beam in ways so that the target physics are beneficial as much as possible, have as much control as we can. That means by controlling the focal profile on the target, by changing the size of the focal profile in time, by keeping very uniform control, and those types of technologies. Those are all important technologies to evaluate because you're trying to find the best type of laser system that you can deliver for the power plant. So again, there's a few things that are left needed, and those are, you know, how scale to the fusion power plant size, the lifetime. I told you thousands, we made a lot of progress. We got from, hundreds to thousands, tens of thousands, maybe hundreds of thousands, still a long ways from a billion shots. It's also very expensive to evaluate on a billion shot time because someone's got to have the time to put in to take all those shots. And it does take time to do lifetime testing. It's kind of expensive thing to do. The other thing is a little bit expensive is to build a very large excimer laser to do the target gain implosion that's going to be needed to evaluate the codes that look very promising. And with that, I think I thank you for all your time and thanks for having me.